Hello students, welcome to EPG Pathshala. I am Mahavir Singh from Physics Department, Himachal Pradesh University, Shimla. Today we are going to talk on module Magnetic Properties of Solid first under the paper Solid State Physics. So students, let us see what we are going to learn in this module. To learn the ferromagnetism, how ferromagnetism originate, and to learn the Weiss theory of ferromagnetism, also to learn the Heisenberg model for the ferromagnetism. So before discussing the ferromagnetism, it is important that we have to understand the Hund's rule. Hund's rule. The Hund's rules as applied to electrons in a given shell of an atom affirm that electron will occupy orbital in such a way that the ground state is characterized by the following. The maximum value of the total spin S allowed by the Pauli exclusion principle, maximum value of the orbital angular momentum L is consistent with the value of spin quantum number S. The value of total angular momentum J, which is equal to L minus S when shell is less than half filled. So when it is less than half filled, so total angular momentum is equal to L minus S, and total angular momentum is equal to L plus S when the shell is more than half filled. When the shell is just half full, the application of first rule gives us L plus 0, so that there is no spin contribution. So the J and the total angular momentum is equal to S. Sorry, when shell is just half full, the application of first rule gives angular momentum equal to 0, so that the total angular momentum is equal to spin quantum number. So this is the Hund's rule, so as to understand the ferromagnetism. Now let us talk about this crystal field splitting. This is also important in context of ferromagnetism, because it is the field which is responsive for the quenching of orbital angular momentum, magnetic moment of angular momentum. The difference in behavior of the rare earth and the iron group salts is that the 4F shell, which is responsible for the paramagnetism in rare earth ions, lies deep inside the ions within the 5s and 5p shell. So 4F shell lies deep in within the 4s and 5s and 5p shell, whereas in the iron group ions, the 3D shell responsible for paramagnetism is the outermost shell. The 3D shell experience the intense inhomogeneous electric field produced by neighboring ions. So this 3D shell experiences a very strong inhomogeneous electric field due to neighboring ions. This inhomogeneous electric field is called the crystal field. The interaction of paramagnetic ions with the crystal field has two major effects. The coupling of L and S vector is largely broken up. So there is no coupling because of this crystal field effect. So the states are no longer specified by the J values. So then there is no meaning of J. Further, the 2L plus 1 sublevel belongs to a given L, which are degenerate in free ion, may now be split by the crystal field. as I mentioned also, due to this crystal field, there is quenching of angular magnetic moment. Now, for ferromagnetic material, when we discuss about ferromagnetic material, after knowing the basic about this Hund's rule and crystal field splitting, the ferromagnetic material exhibit parallel alignment of magnetic moments to one another, resulting in a large net magnetization, which we called a spontaneous magnetization, even in the absence of magnetic field. The atomic dipole moments in ferromagnetic materials is characterized by very strong exchange coupling caused by exchange fields, which results in parallel alignment of atomic moments. Ferromagnetism is strongly temperature dependent, and the magnetization of ferromagnetic material is inversely proportional to temperature in accordance with the Curie-Weiss law. Therefore, ferromagnetic materials have their highest magnetization at 0 degree Kelvin, and the magnetization decreases as we increase the temperature, and at Curie temperature, magnetization of ferromagnetic material disappear, and this ferromagnetic system convert into paramagnetic one.
The Weiss theory of ferromagnetism. Ferromagnetism is the existence of a spontaneous magnetization even in the absence of an external magnetic field. Weiss suggested that magnetic moments are ordered not only by external magnetic field B, but also by the cumulative action of all magnetic moments, that is, elementary moments interact with one another. So this field is named as exchange field. So Weiss named this as a exchange magnetic field and is treated as equivalent to magnetic field BE. This field is proportional to the magnetization M and expressed as BE equal to lambda M, where lambda is constant and is independent of temperature. The effective magnetic field B effective on the atomic dipole is therefore capital B effective equal to B plus lambda M. Since, as we know, this alpha is Jx, which is equal to Gj mu B into B effective over KBT, and this alpha comes out to be Gj mu B into capital B plus lambda M over KBT. As we are interested in spontaneous magnetization by putting B equal to 0, so this equation 4 can be rewritten as alpha equal to Gj mu B lambda M over KBT, and capital M, that is magnetization, comes out to be KB T alpha over Gj mu B lambda. Since magnetization M must satisfy both equation 3 and equation 6, so its value at given temperature can be obtained from the point of intersection of two corresponding M versus alpha as shown in figure 1. So from figure 1, on x-axis it is alpha, on y-axis it is M. So there are three conditions. One is when T is greater than Tf, another is when T is equal to Tf, and another when T is less than Tf. We find that when T is greater than Tf, there is no intersection. It is not matching with the condition as we obtained from equation 3 and 6. Also at T is equal to Tf, again there is no intersection. two curves are not meeting with each other. But when T is less than TF, then we got the intersection of two curves, which comes out to be KBT alpha over GJ mu B alpha. And for alpha very smaller than 1, then this Brillouin function is approximately given by this Bj alpha comes out to be 2j plus 1 into alpha over 3j. So using equation 3, equation 6 and equation 7, we get this Tc comes out to be n mu square lambda over 3 kb, where mu is the total magnetic moment per atom. And this equation 8 is known as Curie-Weiss law. Susceptibility is again temperature dependent. It is also observed from figure 1. From figure 1 that M has only non-vanishing value when T is less than TF. So M has non-vanishing value when T is less than TF, which is linked with the spontaneous magnetization. So for spontaneous magnetization, this T must be less than TF. And for T greater than or equal to TF, the curve does not intersect the lines. So there is no role of spontaneous magnetization, vanishes. So this figure 1 is very important as far as the physics about spontaneous magnetization is concerned. That is, if we want to achieve the spontaneous magnetization, then T must be less than TF. Otherwise, if T is greater than or equal to TF, then this spontaneous magnetization vanish. That is Heisenberg model for the Weiss field. In 1928, Heisenberg had shown that the cause of internal field may be because of exchange interaction between atomic spins. Therefore, the exchange energy of a given atom and its neighbors can be written as U equal to minus 2 Je summation Si dot Sj. This Je is the exchange integral, which is linked with two spins, neighboring spins. Stoner assumed that the instantaneous value of neighboring spins should be replaced by their time averages. If there are z nearest neighbors, then this equation 9 can be written as U equal to minus 2 zje s dot expectation value of s, where s expectation is the average spin of adjoining neighboring atoms. If we assume that the magnetization M as along z-axis, this is the condition that M must act along z-axis, then this average spin value of adjoining neighboring atoms comes out to be M over G mu B into N. And if we put the value of this average spin value, then U comes out to be minus G mu B S into BE, where capital BE is equal to 2Z JEM over N G square mu B square. And if we plot the graph as shown in figure 2, which is known as lateral curve, this graph is between exchange integral JE on y-axis and on x-axis it is RAB over R naught, where RAB is the ratio of interatomic radius, where RAB is interatomic radius, and R naught is the radius of unfilled shell of radius. So if we go through this figure, then on positive y-axis, on positive side of y-axis, which falls iron, cobalt and nickel, which have positive Je, so exchange integral is positive. Also this RAB, ratio of RAB over R naught is greater than or equal to 3. Basically, if this ratio, the ratio of RAB over R naught is greater than or equal to 3, then we achieve the ferromagnetism, which is possible for iron, cobalt and nickel. But on negative y-axis there is manganese whose Je is negative, exchange integral is negative, and for negative side of this y-axis, this ratio of Rb over R naught is less than 3. So that is paramagnetic region. So in broader sense, we can say that on positive y-axis is the ferromagnetic region of this curve, and on negative y-axis is the paramagnetic region. So in paramagnetic region it is manganese, and in the positive y-axis it is ferromagnetic region. Also it is important, this curve is important in the terms that we know that this manganese, which is paramagnetic, but this manganese can be by putting manganese with, say for example, antimony or arsenic or copper. By if we put manganese, if we make the alloy of manganese with antimony or manganese with copper or manganese with Sb, then we can convert this ratio of Rab over R naught greater than or equal to 3. So manganese can be also converted into ferromagnetism, but we have to dope it with either antimony or copper or arsenic. So this curve is technologically important if we want to achieve ferromagnetism from the paramagnetism. Using equation 1, we get lambda comes out to be 2ZJE over Ng square mu b square. Since magnetization of ferromagnetic material is due to spin of electrons, therefore this Tc comes out to be 2ZJE S into S plus 1 over 3 kb. Therefore, from here we conclude from this Heisenberg model that necessary and sufficient condition for ferromagnetism are the existence of incomplete internal atomic shells and have positive exchange integral, because from the curve it is clearly described that this, if we want ferromagnetism, then this exchange integral must be positive, and this ratio Rab over R naught should be greater than or equal to 3. It is possible if the shell are incomplete. Say for example manganese shell is not complete. So if we want to convert from filled shell to unfilled shell, then we have to dope it with copper, arsenic or antimony.
Antiferromagnetism. In antiferromagnetism, the spin moment of the neighboring atom are aligned anti-parallel to each other, hence completely cancel they are anti-parallel, but that is why they will cancel each other, the net magnetic moment. So in this case the exchange integral is negative. So in these material there is no net magnetization. However, when field is applied, small magnetization appears in the direction of the magnetic field. This magnetization further increases with the this magnetization further increases with the temperature and become maximum at critical temperature, which is known as Néel temperature. So basically in antiferromagnetism this transition temperature is denoted by Néel temperature, whereas in ferromagnetism this transition temperature is denoted by Curie temperature. So above Néel temperature magnetization goes on decreasing, which converts this system in the paramagnetic state.
A crystal exhibiting antiferromagnetism may be considered as made up of two sublattices, so that the spin moments of atoms in one sublattice array have an opposite sense from the spin moments of atoms in the other sublattice array. If capital A and capital B are two sublattice arrays, therefore effective field at sites capital A and capital B will be capital BA is equal to capital B minus alpha MA minus beta MB, and capital BB is equal to B minus beta MA minus alpha MB. It is assumed that beside an antiferromagnetic AB interaction, there are also AA and BB antiferromagnetic interactions. So this is also important, that three interactions are important here. One is AB, another is AA, and another is BB. Interactions alpha and beta, three interactions where alpha and beta are Weiss constant, and MA and MB are the magnetization at A and B lattices, such that the total magnetization is the sum of MA and MB. When the temperature is above Néel temperature, then at this temperature paramagnetic state will exist. Therefore, magnetization of sublattices is given as MA equal to capital N mu J square over 3 kBt into capital BA, and MA is equal to N mu J square over 3 kBt into capital BB. The total magnetization M is given as capital M equal to N mu J square over 3 kBt into BA plus BB. Using equation 14 and 15, this capital M comes out to be N mu J square over 3 kBt into 2B minus alpha plus beta into MA plus MB. And if we further simplify, this M comes out to be N mu J square over 3 kBt into 2B minus alpha plus beta into M. And further, M plus N mu J square over 3 kBt into alpha plus beta into M, which is further equal to 2N mu J square over 3 kBt into B. Hence, susceptibility comes out to be mu naught M over B, where the value, if we put the value of M, it comes out to be 2N mu J square over 3 kB over T plus N mu J square over 3 kB into alpha plus beta, and it comes out to be susceptibility equal to C over T plus theta, where theta is the Néel temperature. And this equation 19 is analogous to Curie-Weiss law, and in the absence of magnetic field, that is B equal to 0, and when theta is equal to T is equal to Tn or theta is equal to Tn, so basically Tn is the Néel temperature, then this Ma comes out to be N mu J square over 3 kB Tn, and which is equal to minus alpha Ma minus beta Mb, and Mb is equal to N mu J square over 3 kB Tn into minus beta Ma minus alpha Mb, and 1 plus alpha N mu J square over 3 kB Tn into Ma plus beta N mu J square over 3 kB Tn Mb is equal to 0. And further, 1 plus alpha N mu J square over 3 kB Tn Mb plus beta N mu J square over 3 kB Tn Ma is 0. Since C is 2N mu J square over 3 kB, so therefore C over 2 Tn comes out to be N mu J square over 3 kB Tn. Substitute this value in equation 5 and 6, we get Tn equal to C beta minus alpha over 2. This is important relation. It is evident that as Néel temperature increases, AB interaction beta, as Néel temperature increases, this AB interaction beta becomes stronger, and it decreases with increasing AA and BB interaction. So this is important, that this as Tn increases, meaning thereby AB interaction increases, AB interactions become stronger, and if Nil temperature decreases, it strengthen the AA and BB interaction. Also, this is important. If we plot the graph between susceptibility versus temperature, on axis it is temperature, on y-axis it is susceptibility, then the difference between this ferromagnetism and antiferromagnetism is that there is enormous increase in ferromagnetic susceptibility obtained at Curie temperature.
So students, let us now summarize what we have learned in this module. We discuss about Hund's rule, how Hund's rule is important in order to discuss the about the paramagnetism and ferromagnetism. Then we also discuss about crystal field splitting. Through this concept, we came to know that how 3D experience intense strong field, and due to this field sometimes there is quenching of orbital angular momentum. Then we also know about the ferromagnetism, that how ferromagnetic material have spontaneous magnetization. Then what is the cause of spontaneous magnetization? We also discussed that antiferromagnetic material, the spin moment of a neighboring atom aligned antiparallel, so the net magnetic moment is 0 in the absence of field. But definitely if we apply the field, then they experience some amount of magnetization. Then we also discuss the Nil temperature. In the case of antiferromagnetism, Nil temperature is the transition temperature below which the system is in antiferromagnetic state, where susceptibility increases, and at the transition temperature, at Nil temperature, system convert from antiferro to paramagnetic. And through Nil temperature, if Nil temperature increases, the AB interaction which is denoted by beta, and if Nil temperature increases, this AB interaction becomes stronger. Whereas if Nil temperature decreases, then then AA interaction and BB interaction, which we represent by alpha, also decreases. Thank you.